Understanding reforming chemistry begins with the catalyst itself. For this example, we will explore a spherical bead used in continuous catalytic reforming. Made from high-purity alumina gel, this bead measures about 1.6 millimeters in diameter, about the size of the tip of a ballpoint pen. To appreciate the chemistry, we need to journey to the atomic scale, into the labyrinth of pores where the reactions occur. This is a macropore, a veritable highway about 200 nanometers wide, where the process gas flows and interacts with the many alumina crystallites. However, the majority of reactions occur between these crystallites in even smaller channels. The glowing lights represent the platinum clusters, which we will soon see play a vital role. But first, let's focus on a single alumina crystallite. Measuring roughly 20 by 10 by 5 nanometers, the crystallite's reactive surfaces contain oxygen and aluminum and provide a platform for the platinum clusters. Adding water to the process feed forms hydroxyl groups, or acid sites, which increase logarithmically as the water concentration is increased. For now, we will use a typical water partial pressure of 25 pascals. Hydrogen chloride is added in a precise ratio to supply the requisite chlorine sites, shown in green, which promote the acidity of the neighboring hydroxyl groups. Let's zoom further to observe the dynamic equilibrium on the surface. Here, a water molecule reacts with the alumina to form two acid sites, which can then either recombine to form water or can be displaced by a chlorine atom. Water can, in turn, reverse this reaction. Meanwhile, hydrogen dissociates and recombines on the platinum cluster. Thus, we have a dynamic equilibrium. To demonstrate the main reforming reactions, we will follow a single, fully saturated N-hexane molecule. As it reaches a platinum cluster, two hydrogen atoms are removed, leaving behind a carbon-carbon double bond. The olefinic molecule then becomes protonated by an acid site, while the platinum removes two more hydrogens, allowing ring formation. This intermediate methyl cyclopentane expands and dehydrogenates further to form benzene, a desirable product. Ring formation isn't the only possible outcome. The same olefinic molecule can branch through a protonated cyclopropane mechanism on an acid site. Subsequent hydrogenation yields a saturated 2-methylpentane, another desirable product. Before leaving in the product stream, this same molecule can undergo unwanted side reactions. In this case, it becomes dehydrogenated before encountering an acid site, where it cracks into two propenes. Cracking isn't limited to acid sites. It can also occur on a platinum cluster. Here, N-hexane becomes triply bound to the platinum, which then severs the terminal carbon, forming methane and N-pentane. Looking back at the various outcomes of the N-hexane molecule, we first saw it undergo dehydrogenation on a platinum crystallite. From here, it can undergo ring closure and expansion to become benzene through a methyl cyclopentane intermediate, or undergo branching to form 2-methylpentane. These desirable high-octane molecules can crack on either acid or metal sites, forming less desirable low-octane molecules. Other hydrocarbons undergo their own array of transformations, relying on the vast surface area of the alumina gel and the delicate balance between acid and metal functions.